Why can't an airplane use gasoline like a car? The question seems simple, almost logical, and yet it hides one of the greatest misunderstandings that exist among the general public about how aviation really works. Imagine a common scene at any airport in the world. An aircraft parked on the apron, still motionless, while the light of dawn begins to make its way through. Beside it, a fuel tanker truck connects enormous hoses directly to the wings. In that everyday gesture, something already appears that does not fit the logic of a car. There is no smell of gasoline, nor does the familiar click of a fuel nozzle appear. Nothing in that image refers to a typical gas station. Through those pipes flows a completely different fuel, designed to withstand pressures, temperatures, and demands that no automobile engine would ever face. And in that detail, almost invisible to someone watching from the terminal, it is already suggested that the logic of fuel in an aircraft belongs to another world. At first glance, it might seem that an airplane and a car, being machines that move, should not differ too much in the type of fuel they use. However, in commercial aviation, the exact opposite occurs because gasoline proves volatile, dangerous, and unstable under the extreme conditions in which an aircraft operates. And even so, that explanation is not enough. It is not enough to point out the risk that it could ignite. Behind it lies a precise combination of physics, chemistry, and engine design that makes gasoline literally incompatible with modern aviation. To understand it, one must look at a place that is not intuitive. What really happens to fuel when an aircraft climbs toward the extreme cold and low pressure of the atmosphere? When an aircraft gains altitude, the problem is not only the cold or the low pressure, but how those conditions alter the behavior of the fuel. What on the ground seems like a stable and predictable liquid can, in flight, evaporate prematurely, form bubbles within the system, and lose continuity precisely where it is most needed. It is in that transition, silent yet critical, where gasoline ceases to be a viable option for a commercial aircraft. Already at cruising altitude, the environment no longer resembles in any sense that of a car on the road because the fuel no longer circulates within a short and simple system. It travels through long and complex lines, subjected to constant vibrations and very severe thermal changes, while atmospheric pressure drops drastically and encourages the formation of vapors within the system. At the same time, external temperatures descend to extreme levels. Under these conditions, any fuel that does not maintain stable behavior becomes unpredictable. That is why aviation requires a type of fuel capable of preserving its properties, even when the aircraft moves through one of the most hostile environments on the planet. Gasoline in this context is an incompatible fuel. Its main problem is its extreme volatility. At low pressure, it vaporizes very easily, generating bubbles that can block pumps, pipes, or filters. This behavior, known as vapor lock, is extremely dangerous in systems that depend on a continuous and stable flow to feed the engines. In addition, its low flash point causes it to generate flammable vapors very easily, a risk that intensifies when pressure decreases and environmental control is limited. In contrast, kerosene is designed precisely to operate under these conditions. It is less volatile, more stable, and maintains predictable behavior even in environments with greatly reduced pressure. Even in that context, at extremely low temperatures, small crystals can form, but commercial aviation uses additives and heating systems that keep the fuel within safe operating ranges. The entire fuel system of an aircraft, from the pumps to internal recirculation, is designed exclusively around these properties. The difference does not lie in the engine, but in the fuel that feeds it, because even before reaching the combustion chamber, gasoline already poses unacceptable risks in commercial aviation. Under those same conditions, kerosene remains manageable, uniform, and reliable, an essential quality for an aircraft to operate safely where any system designed for an automobile would fail. Under those same conditions, kerosene remains manageable, uniform, and reliable, an essential quality for an aircraft to operate safely where any system designed for an automobile would fail. With all this on the table, an inevitable question arises. What would happen inside a turbine designed to work with a completely different fuel? If one observes how a jet engine works, intuition begins to break down. It is not about successive explosions, as in a car engine, but rather a continuous and extremely delicate process. Air enters through the compressor, passes through several stages in which its pressure increases progressively, and finally reaches the combustion chamber, where it mixes with the fuel and sustains a constant, stable, and controlled flame. In that environment, any sudden variation is critical. If combustion ceases to be uniform, if the flame becomes irregular or unpredictable, the engine's balance is lost almost immediately. Abnormal vibrations appear, performance drops, and in the worst case, the turbine shuts down abruptly. It is at this point that it becomes evident that not all fuels can behave in the way a turbine requires. Gasoline, in that context, presents a clear problem. Its combustion is too rapid, and its volatility so high that when mixed with compressed air, it produces almost instantaneous ignition, very difficult to control within a combustion chamber designed for a progressive flow. That type of combustion can cause sudden hot spots and abrupt pressure changes that damage the turbine blades. In that type of engine, operation is based on synchronized explosions. Gasoline fits into that logic because it releases its energy quickly, in a concentrated and repetitive manner within a closed space. And it is precisely for this reason that gasoline fits so well in piston engines, where its explosiveness is harnessed in small controlled cycles inside closed cylinders. In a turbine, the exact opposite occurs. There are no successive explosions, but rather combustion that must remain continuous and stable, almost like a permanent torch inside the engine. Attempting to replace kerosene with gasoline would be like feeding a bonfire with a fuel that is too volatile. The flame loses uniformity, becomes unpredictable, and ceases to behave as the engine requires. For this reason, a jet engine simply cannot operate that way. And although with this we would already have sufficient reasons to completely rule out gasoline, there is still an even more concerning aspect to consider: fuel storage. Because if gasoline proves dangerous inside the engine, it is even more so when thousands of liters are transported under the wings in a high-risk situation marked by pressure, vibrations, and constant thermal changes. This leads us to the next question. What would happen when transporting gasoline in gigantic tanks under the wings of an aircraft where any leak, vapor, or spark could trigger an even greater risk? When fuel is stored in large quantities, the problem ceases to concern only the engine and shifts to the interior of the system, inside the tanks, where gasoline generates vapors with enormous ease and occupies the space above the liquid. This phenomenon is not limited to aviation. In a car, this same effect already requires ventilation and control systems. When that logic is transferred to an aircraft, with tanks that can far exceed tens of thousands of liters, the accumulation of vapors becomes unmanageable and completely changes the scenario. Under those conditions, even a minimal variation in temperature can increase the internal pressure of the tank and the amount of vapor present, creating highly flammable mixtures. An open flame is not necessary for something to go wrong, because static electricity, friction, or an inadvertent discharge may be enough to cause a serious accident. And it is at this point that it becomes evident that a fuel as volatile as gasoline not only compromises the operation of the aircraft, but also its storage, its refueling, and ground safety. Added to this risk is a key factor. The flash point of gasoline is extremely low, much lower than that of kerosene. This means it can begin to release flammable vapors at relatively mild temperatures, something completely incompatible with a system subjected to the thermal variations of flight and the ramp. Kerosene, by contrast, requires significantly higher temperatures to generate flammable vapors, which drastically reduces the risk during storage and ground operations. Refueling would be another critical scenario. When an aircraft receives fuel, there are ground personnel, electrical equipment, moving vehicles, and multiple operations taking place simultaneously around the aircraft. With gasoline, the area could quickly fill with invisible and dangerous flammable vapors. Every vehicle, every piece of operating equipment would represent a real risk. Operators would have to work under far more restrictive and slower procedures, increasing both turnaround times and the possibilities of human error. And even then, gasoline would continue to be a constant risk factor. There is also the scenario of physical incidents. An impact with a ramp vehicle, the fall of equipment, or even a harder-than-expected landing can cause structural damage to the tanks. If those tanks contained vaporized gasoline, the probability of ignition would be much higher than with kerosene. It is not that kerosene is safe in an accident, but rather that it is far less prone to ignite suddenly. For this reason, aviation adopted it, not because kerosene eliminates risk in an accident, but because it provides a stability that limits the probability of ignition even in infrequent yet inevitable scenarios. Gasoline, by contrast, would represent an unacceptable danger in large-capacity tanks, both because of its volatility and ease of ignition, and because of its sensitivity to thermal changes, pressure, and friction, conditions that make it incompatible with this type of system. But safety is not the only criterion at stake. If fuel must also be efficient, how does the difference between gasoline and kerosene influence an aircraft's actual range? In flight, that difference translates directly into range. An aircraft's endurance is not determined solely by the engine or aerodynamic design, but by how much usable energy it can carry and manage without penalizing weight, performance, or safety. And it is in that balance that kerosene became the standard, not because of an isolated advantage, but because of stable and predictable energy behavior under the extreme conditions of flight. The practical difference appears in design and operation. An aircraft that used gasoline would have to incorporate more complex and heavier systems to control vapors, pressures, and ignition risks. More systems imply more weight, more maintenance, and greater structural compromises. All of this would ultimately affect the aircraft's range, payload capacity, and overall efficiency, especially on long-haul flights where every kilogram and every liter matter. At high altitude, where temperatures drop drastically, these differences become even more relevant. Gasoline, due to its high volatility, tends to generate vapors and less predictable behavior within the fuel system, making it difficult to maintain stable supply during prolonged cruise conditions. Kerosene, by contrast, preserves thermal and operational stability that allows for constant combustion and sustained thrust without unwanted fluctuations in performance. This stability has a direct impact on airline economics. Transporting fuel efficiently makes it possible to maximize range without reducing payload or unnecessarily increasing consumption. Every additional kilogram penalizes performance and increases operating costs. Kerosene allows most of the fuel carried on board to translate into usable energy, something essential for maintaining long routes, controlled costs, and precise operational margins. A hypothetical scenario illustrates this clearly. A long-range aircraft designed to travel more than 12,000 kilometers using gasoline would require additional systems to manage vapors, pressures, and safety risks throughout the entire flight. That increase in complexity would affect the aircraft's weight, structural design, and overall efficiency. Gasoline would be a fuel more difficult to manage, more volatile, and less compatible with prolonged and stable operations. In that context, long-haul commercial aviation would cease to be viable as we know it today. And yet, there is a common source of confusion. There are small aircraft that do use gasoline, piston engines, light aircraft, training models. If that is possible, why does commercial aviation discard it completely? What exactly changes when an aircraft stops being small and begins operating on a different scale? Although in commercial aviation it would be impossible to use gasoline, there is an exception that often creates confusion: small planes and light aircraft that do operate with similar fuels. But this exception does not contradict anything we have seen so far. On the contrary, it confirms the rule, because these aircraft do not use automotive gasoline, nor do they operate in the same environment as a commercial aircraft, and what works on a small scale becomes unviable, dangerous, and inefficient when conditions change completely. Aviation gasoline, known as Avigas 100LL, is a fuel specially formulated for piston engines. Its name comes from aviation gasoline, and the designation 100 low lead refers to its high octane rating and low lead content. It has a much higher octane rating than automotive gasoline, carefully controlled stability, and additives designed to prevent detonation in cylinders subjected to high demands. Avgas is intended for small engines that operate through repeated explosions, not for turbines that require continuous and stable combustion. In addition, it is designed to operate at moderate altitudes, where pressure and temperature variations are not as extreme as in high-altitude commercial flights. Light aircraft fly in a completely different ecosystem. They operate at much lower speeds, at low altitudes, and for shorter flight durations, which entirely conditions the way they store and manage fuel. The tanks they use are small, and this drastically reduces the accumulation of vapor inside them. The difference between a 100-liter tank and a 20,000-liter tank is not merely a matter of scale, it is a change in the physics of the fuel. With such reduced volumes, the risks of vapor lock, excessive evaporation, or dangerous vapor mixtures remain within manageable margins. For that same reason, the fuel systems of these engines are also simpler. They do not require extremely high-pressure pumps or combustion chambers that depend on absolute stability to function properly. But even with the aforementioned, it is necessary to add the fact that aviation gasoline has significant limitations, especially when conditions become demanding. In very hot climates, it can form vapors that make starting difficult, and at higher altitudes, its behavior becomes less predictable, in addition to the fact that piston engines are much more sensitive to thermal variations. For that reason, light aircraft that use avgas operate under specific procedures to avoid vapor lock and ensure a constant fuel flow, systems that would not be suitable for a large aircraft, where the energy and stability requirements are completely different. This exception cannot be transferred to commercial aviation because in a large aircraft, the use of gasoline would completely alter the functioning of the system. It requires incorporating much larger tanks, increases the risks and reduces the range, while introducing serious problems in storage and refueling. In addition, jet engines are not designed to operate with this type of fuel, which makes the operation unsafe and inefficient. Commercial aviation is only viable because it uses kerosene, a stable, safe and efficient fuel capable of sustaining engines that must operate for hours under extreme temperatures and pressures. It is enough to imagine two scenes that could not be more different. On the one hand, a light aircraft refueling with avgas at a small airfield with a simple engine, small tanks and calm conditions. On the other, an intercontinental aircraft loading tens of thousands of liters of Jet A, surrounded by vehicles, ramp personnel and simultaneous operations. They are different worlds, and what is safe in one would become extremely dangerous in the other. And yet, both in light aircraft and in commercial airplanes, there is something that does not change: the critical importance of those who supervise, control, and certify the fuel that enters each aircraft. That is why the natural question now arises. If fuel is so critical to the safety of any flight, who are the people responsible for ensuring that every drop is in perfect condition before takeoff? Behind every takeoff, behind every hour of flight, and behind every fuel system that works as it should, there are people who monitor, verify, and certify that everything is in order. If fuel is one of the most critical elements of an aircraft, it is because it depends not only on its chemistry and stability, but also on the precision with which the professionals who handle it perform their work. And it is they, more than any technology, who guarantee that each aircraft can take off with complete safety. Aeronautical mechanics are the first line of defense. Before the fuel reaches the engines, it is they who inspect the fuel lines, valves, filters, pumps, and pressurization systems. They walk beneath the wings and scan the fuselage with a trained eye to detect any sign that an inexperienced observer would overlook. A faint, unusual smell, an uncommon vibration, a joint that does not seem as firm as it should, can be indications of a problem that must be resolved before authorizing the flight. Their responsibility is immense, and each inspection is an essential link in the safety chain. Then there are the fuel inspectors, specialists whose work is invisible to passengers but absolutely crucial. They are the ones who analyze samples of the Jet A that is going to be loaded onto the aircraft, ensuring that there is no presence of water, particles, contaminants, or any irregularity that could compromise its quality. These professionals work under extremely strict protocols. If a result is not perfect, that batch of fuel is rejected without discussion because kerosene, although very stable, must meet rigorous standards to safely power engines that operate at extreme temperatures and pressures. Parallel to these controls, the work of the fuel teams and ramp operators comes into play, responsible for the physical refueling process. They are the ones who connect high-flow hoses, control fueling pressures, supervise anti-static grounding, and coordinate each step with the crew and operations control in a process that requires constant precision and absolute coordination. In this type of operation, nothing is left to chance. From the approach of a vehicle to the regulation of the flow rate, every movement is strictly regulated because an error at this stage would not only delay a flight, which is no minor matter, but could also create a real risk in an environment where people, vehicles, and highly sensitive systems coexist. This entire process can be imagined as an everyday scene. An aircraft remains parked on the apron, still warm after its previous flight, while beneath the wing, one operator connects the grounding cable to dissipate static electricity, and another checks the pressure in the line. Nearby, an inspector holds a transparent cup containing a sample of Jet A and observes its clarity, its color, and the absence of bubbles or sediment, while at the same time a mechanic walks along the fuselage with a flashlight, inspects an access panel, and ensures that there are no signs of leakage. Each one fulfills their role with precision, without unnecessary haste but without a single second of carelessness. It is work that goes unnoticed, that no one sees or applauds, yet without it no flight would be possible. Fuel is an essential part of aviation, although it is not merely a matter of chemistry or efficiency. It is, above all, a matter of human responsibility. Systems may be automated, engines may be robust, and kerosene may be stable, but in the end, it is people who ensure that everything functions as it should. They are the ones who detect the details, confirm the quality, and supervise the procedures that keep operations within safe margins. In the end, aviation is sustained not only by brilliant engineering or advanced technology, it is also sustained by people, by expert hands and attentive eyes that work in silence, consistently and rigorously, so that every aircraft can take off with the safety we take for granted. And behind that human work appears inevitably the same question with which everything began. Because flying is nothing like driving. Before takeoff, an aircraft's fuel must withstand conditions that no car ever faces: extreme temperatures, very low pressures, precise flow rates, and engines that demand stable combustion for hours. In that context, gasoline, with its volatility and low flash point, becomes a constant risk both in flight and on the ground. All of this leads us to a clear idea. Kerosene is not a technical curiosity or an inherited custom. It is the energy foundation upon which commercial aviation is built. Thanks to it, an aircraft can maintain stable flight for hours, cross entire oceans, and operate with extremely high safety margins. Gasoline, by contrast, would break all these guarantees, from engine performance to storage safety and operational efficiency. From that point on, the perspective changes. An aircraft on the apron is no longer just a machine waiting to take off. Every connection, every procedure, every inspection begins to make sense. Fuel ceases to appear as a simple, flammable liquid and reveals itself for what it truly is, a critical element designed to function under conditions that no other system faces. What once went unnoticed becomes visible, not as a spectacle, but as a silent part of everything that makes flight possible. Thus concludes a journey through a topic that seemed simple but has proven to be surprisingly deep. And if you are interested in continuing to explore that hidden world behind aircraft, discovering how the machines that move the world truly work and the systems that keep modern aviation in the air, subscribe and join us in the upcoming videos. Here, we will continue unraveling the technical principles that make the impossible possible every day.